Founded in 2010, SOAR is a student-led high school enterprise team from Dollar Bay, specializing in ROVs, remotely operated vehicles. SOAR allows students to gain experience in areas such as coding, design, manufacturing, and troubleshooting. Each day, challenges are taken where failure happens often and in front of peers. However, we want to learn from these mistakes, no matter how common they may be. Our main focus is providing technical solutions within our community. Today, we will be talking about our compact ROV, buoy ROV, rookie ROVs, and our Isle Royale ROVs.
Hi, my name is Joshua Gaunt and I'm currently working on our compact ROVs. The compact ROVs are going to be used to explore areas such as underwater mines and inland lakes. Smaller versions of all the parts are used from our Isle Royale ROVs. One of the problems I was having was calibrating the smaller ESCs, electronic speed controllers. The difference between them and normal ESCs is that they do not have a set key button. This button allows the ESC to go into calibration mode. To work around this problem, I changed the range of values that the Arduino Uno was sending to the small ESCs instead of changing the calibration of the ESCs. Another problem I am currently having is the communication between the two Arduinos. On the compact ROV, there are two Arduinos. One is an Arduino Uno that stays on the land, and the other is a mini Arduino that's inside the ROV. They communicate using RS485 communication chips. My first thought was that the chips are not working properly. To test this, I uploaded transmit code to the Arduino Uno and receive code to the mini Arduino. Then, I connected the chips to their respective Arduinos and the chips to each other. Then, the transmit Arduino light blinks a random amount of times, and that same amount of blinks is repeated on the receive Arduino. And finally, I switched the chips to be connected to the other Arduino and tested again. That worked, so I knew my chips were not the problem.
Hi, my name is Clayton Downs, and I'm currently a rookie. When you first join SOAR, you start off as a rookie. Your goal is to design and create an underwater robot that's job is to retrieve a T. Rookies start off by making a spreadsheet with all the parts they think they might need with a budget of $400. Then, once they finish their building, they get to building. Their learning steps start off with them building a frame of PVC pipe. We have an example of that right here. Then, after that, they begin learning basic circuit skills. Then they will move on to more advanced skills such as 3D modeling and printing and soldering wires to the motors of the ROV. Then, some small finalizations like making it buoyantly neutral and some troubleshooting. Then, once the snow melts, they head out to our Coast Guard station and try to retrieve a T from the bottom of the lake. Most attempts are unsuccessful, but failure is a big part of engineering. Rookies learn valuable skills that they will use later.
Go whenever.
Hi, my name is Andy Anderson, and this year as a rookie in the SOAR enterprise, I've gained many life skills. For example, I've learned how to budget, 3D print, create circuits, and program. When I'm 3D printing, one of the problems I've been having are the measurements. When we physically measure diameter to create a part in the code, we use radius instead. If the diameter is used, the part will be much larger than needed. Another problem I've been having are the printers failing. There are many things that could go wrong with a printer. Some things that have gone wrong are connecting to the printers, filament being too thin or too thick, and printing when there's no support, which means you're printing in the air, and that is not good.
All right, ready? Hi, my name is Jasper Lee, and I'm working on an SSROV, or semi-submersible remotely operated vehicle. The basic idea is to have an exploratory vehicle hanging down from an independently floating buoy. This configuration accomplishes two main goals. First, it can take a relatively accurate location of the ROV and record what is being observed underwater because the surface buoy is in close horizontal proximity to the submerged vehicle and can utilize GPS. We are able to investigate specific underwater coordinates which would otherwise be complicated by wind and underwater currents with a traditional fully submerged ROV. All right. The second benefit is that of increased range and mobility. The range from the user is limited by radio transmit distance, much less restrictive than a limited length tether. It is also free from annoying tangles and kinks, things that often plague tethered vehicles. The SSRV has two primary parts connected by a tether, a submerged vehicle and a surface buoy. The submerged vehicle has 2 thrusters for rotation control around the vertical axis, an onboard power source, and a camera. This vehicle is connected to a buoy by a tether that can extend down to 120 feet for vertical control. The surface buoy includes a tether winding motor, a tether spool, an indicator light, an RC receiver and camera receiver, an onboard power source, and 2 thrusters for translational horizontal control. A GPS receiver is also in the process of being added. The system is controlled by 3 Arduinos. The key design difference is the RC user interface rather than a wired Nintendo controller used by some of our other projects. That really allows us to go out and use that increased range for the new objectives that we're trying to accomplish.
Hi, I am Noah Halkola, and I'm currently working on the Isle Royale ROVs for the SOAR enterprise. Over the past few months, I've been working on getting a broader understanding of this ROV to our students and our buyers, so they can also begin to improve on problems that become imminent. So far, I've had to go through rigorous self-taught and peer-taught troubleshooting, as well as creating solutions to our backplate problems in order to fix the problems seen by the park rangers we sell to. I will now show you a presentation slide of the problems that have come up with the ROV in the past couple months. The most present of these issues is the delamination of our epoxy resin around the wires on the back of the ROV, which eventually means water could leak through over time. And the process to recreate this backplate is difficult, and the fogging up of this camera lens is also due to the high humidity. The solution we have come up with is to instead epoxy the connectors of the wires to the plexiglass itself, still giving us a watertight seal and leaving less room for the delamination of the wires. This will also leave room for us to install a vacuum seal, which will allow for the camera to not fog up. Thank you for watching our presentation today.